welcome back and thanks for checking in. This is your latest video lesson for working with the Pythagorean Theorem, which we've been working with for about a week now. And today's target is that hopefully you will be able to apply the Pythagorean Theorem to 3D, right? That means three-dimensional shapes. Now, real quick, let's not forget what the Pythagorean Theorem is. This is a Pythagorean theorem, right? A squared plus b squared equals c squared, where a and b are the legs, right? And they make that 90-degree angle. And c over here is the hypotenuse, which is always the longest side of your triangle. And it is opposite of the 90-degree angle. So those are just some things that we've been talking about over the last week about the Pythagorean theorem. And of course, it is only used with right angles, right? Well, the interesting thing is that up until this point, we've been working with two-dimensional shapes, just like the triangle that you see here, right? It's got length and width, but no depth, right? That's a two-dimensional figure. And what is interesting is that when we consider three-dimensional objects, like prisms or cylinders or cones or pyramids, even though they're three-dimensional and they've got length and width and depth to them, they do actually have, a lot of them have right triangles within them. So I'm going to teach you how to take this idea, this concept of the Pythagorean theorem and how it works for right triangles. I'm going to teach you how to take that and apply it to three-dimensional shapes. So again, we're talking about pyramids and cones and cylinders and things like that. So I want you to try to get your eyes ready for finding these right triangles that are kind of hidden within these three-dimensional figures. And here's the first one, so you can kind of get an idea of what I'm talking about. We're going to try to figure out the height of this pyramid. Well, that's a three-dimensional object. A three-dimensional figure. It's not a triangular pyramid. That is a rectangular pyramid. The base is a rectangle. That's a rectangular pyramid. And the height of the pyramid is not 25, and it is not 14. The height of the pyramid is the distance from the center of the base, right here, straight up to that vertex, that highest point within the pyramid. That is the height. So it's kind of hidden, if you can imagine, hidden in the middle of the pyramid. So if you could step inside that pyramid and go stand right in the middle of the floor and look up at the ceiling at the very highest point, that's the distance we're going to try to calculate. They do not provide that distance for us in this design. They tell us, though, that this length is 14. And they tell us that this length, which is called slant height, is 25. Now, all those calculations, all those measurements are useful, and they're going to help us figure out the measurements that we actually need for this right triangle. Okay, so you have to imagine that you're just looking at that right triangle within that pyramid. I need to know at least one of the legs, and it looks like I already know the hypotenuse. Okay, so I'm going to say this is leg A, and this is the one I'm trying to find, which is the height of the pyramid. And this is leg B down here. And then the hypotenuse over here is, again, that side, that slant height, that is 25. All right, so I'm trying to find A, and I kind of know the measurement of B. So if I'm going to redraw this triangle here, just so you can see it maybe outside of the shape. Okay, there's my 25. Here's my A, there's my 90 degrees, and here's my B. Now, B is not 14. B is actually 7, right? This distance from out here on the edge to the center of the base, right, standing in the middle of that room, would actually be half of that 14. So that would actually be 7. So there's my triangle. Now, I know B, and I know C, and I don't know A. So let's write our formula. A is the side that I'm trying to find, which is the height of the pyramid. B is 7, which we're going to square, and C is 25, which we're going to square. 7 squared is 49. 25 squared is 625. I'm going to subtract that 49. So that happens. That leaves me with A squared equals 576. You should know by now that to find A, we need to take the square root of 576. And it's a nice whole number. It's 24. So the height of this pyramid is 24 whatever, meters or inches or feet or whatever unit is that we would be measuring in. And I'm really not concerned with units today. I'm mostly concerned with the math behind all this, making sure that you can find those right triangles, label the legs, label the hypotenuse, and then plug them into the formula and solve as needed. Let's do this one. This is a cylinder, right? So this is like a can of soda or a can of soup. And there is, in fact, a right triangle here. Here it is. That all the way across there, which is the diameter of that base, and then this diagonal that cuts all the way through the cylinder. So there's my right triangle. What measurements do I have? I know that from A to B is 8 centimeters, and I know that from B to C is 15. Those are the legs, right? There's your right angle right there. And it looks like I'm trying to find X, which would be C, the hypotenuse. So let's plug in. A squared plus B squared is going to equal C squared. 64 plus 225 is 289. I got to take the square root of that. You guys should know all that by now. And on your calculator, when you take the square root of 289, you figure out that it is 17. And in this case, they do provide a label. It is 17 centimeters. Let's check and see if that makes sense. If that is 17 and that's supposed to be the longest side, is it the longest side? A disco. It most certainly is, and most likely you are right. If you ended up with a measurement less than 15, then you would hopefully catch the fact that you must have made an error, right? Because C, the hypotenuse, always has to be the longest side of your right triangle. Let's look at this guy. Okay, you heard me earlier talk about slant height, and it comes up again in this problem. It says find the slant height of the cone. All right, well, slant height just means the height or the length of the part of the three-dimensional figure that is slanted. So in this case, they tell us the height of the cone, right, from the vertex down to the center of the base is 12. And then we know that from the center of the base out to the edge of the cone is 5.7. So those are your legs. You know A and you know B. What you don't know is H, otherwise known as C. And this is what we call the slant height. It's like the slanted side of the cone. Or, in the case of this right triangle, it's the hypotenuse that we don't know. They give us the legs, we need to find the hypotenuse. Those are actually the easy ones. What's A? A is 12. What's B? 5.7. 12 squared, 144. 5.7 squared. I add those two together. Now remember, to find C, you got to square root that mess. And on a calculator, round it to the nearest tenth. 13.3 centimeters would be the slant height. Now check it. Is that the longest side? Because it needs to be. Yes, it is. Well, we are down to just one more example of how to use the Pythagorean theorem and apply it to three-dimensional figures. This is the last one we're going to do. This is a prism. It's a rectangular prism. And lo and behold, there is a right triangle hiding within. Little tricky to see this one. So we've got this leg here from A to C. And then we've got the other leg that goes from C to B. And we've got the hypotenuse that goes from A across and down to B. So we've got this right triangle. Now, we need to figure out some measurements here. And this is kind of a tricky problem because it's actually two problems in one. You know the height from A to C is 12. That's kind of hiding right there. So I know that is 12. But I don't know the measurement from C to B. I do not know this piece right here. So first I have to solve another Pythagorean theorem problem to figure out what the distance is from C to B. This, again, I'm talking about this distance right here. We don't know that measurement, and we need to know it. Well, I see another right triangle hiding within. Do you see this one? Now, I realize it's on the angle, but that is actually a right triangle. That is a little right triangle like this. This is a 3, this is a 4, this is the C, this is the B within the shape, right? So, we've been working with the Pythagorean theorem. We're trying to find this distance here right now, which would be the hypotenuse. So you've got 3 squared plus 4 squared equals C squared. Hopefully you, well, maybe, I shouldn't say hopefully. Maybe you recognize this to be a special right triangle that we've worked with before. This is called a 3, 4, 5 right triangle. So that's a 5, which means that measurement right there is 5. So I actually had to use the Pythagorean theorem to find one of the measurements I need. Now I have to use the Pythagorean theorem again for the bigger triangle to find that big diagonal right there. Now I know that's 12. I found that measurement to be 5, and now this is the one that I'm really supposed to be solving for, that dashed line. So again, here we go. A squared plus B squared, right? Those are the legs. That's what I get when I square my legs. I got to take the square root of it to figure out what C is. C is 13, which is in fact the longest side and is probably an accurate measurement, which means you probably did it right. So this was an interesting problem because it was actually two problems in one. The first thing you had to do was use the Pythagorean theorem to find that missing value. And then once you knew that, that went there, right? That became one of the legs of the bigger triangle because ultimately we were trying to find that dotted line. That was the ultimate goal, which ended up being that answer. So you had to use Pythagorean theorem twice. Holy cow. Well, guess what? Of course we're going to be working on an activity or a worksheet of some kind in class so that you can work on applying the Pythagorean theorem to three-dimensional shapes. And sometimes it's just a matter of getting your eyes kind of set straight and doing a little investigating to find some of the measurements that you need, and then you plug them in the formula and make it work for you. All right? Hey, awesome. I'll see you in class.